Hey, hi everyone. Thank you everyone for being here, and thanks to the organisers for setting this up and allowing me to speak. So today I want to talk about some work I did last year, which, as from the title, we probably see is related to higher categories. Though I'm hoping that it's not going to rely on too much theory, and I'm going to go over everything pretty slowly. And yeah, I'm really hoping that this is going to be accessible. So I assume the hosts are watching for hands up. If there's any questions, I'd be happy to answer them as I'm going through. So yeah, let's just get started. So great, this is working. So yeah, I want to start off by talking about going over the theory of globular sets, just going over their definition, defining them for anyone who hasn't seen them before. And then I want to move on to different sorts of composition operations you can see in these globular sets. And finally, I want to talk about the work I did, which is sort of defining this Whisker-based composition scheme for globular sets. And the idea is, we'll see the idea later, I think. It'll be easier to explain once we've got some definitions. So before we get too much into anything, I'm going to sort of try and motivate what I'm doing a bit. So what is higher category theory all about? So regular one category theory, as I'm hoping everyone knows since you're at a category theory symposium, consists of objects and arrows. And then the idea of higher category theory is we want to allow higher arrows between these arrows, but that's sort of a wishy-washy definition, and well, it's not a definition. And in fact, there's lots of different things we could do in a scenario. So for example, we could have things that look like, so I'm going to try and write. So we could have things that are simplicial, which look like triangles. So if the lines are 1 arrows, then we can have 2 arrows between them. We can have things that are cubical, where we have things like these squares. And we've seen some talks involving double categories earlier this week, which fall into this sort of system. We can even have things like this that look like many to one trees, which I'm not going to be able to draw anything higher than 2 dimensions, and I don't know much about it, so please don't ask too many questions on this. But today's talk, we're going to focus on globular sets, and these arrows look like this. So I've drawn a 2-dimensional arrow here. So the idea is that these dots, I can use them. You can see the mouse, right? Can someone nod if you can see the mouse? Okay, just go with that. So the idea is that these dots here are the objects, and then these lines, which I haven't drawn an arrow tip on, but the idea is that these are the one morphisms or arrows from between the objects, and then I've drawn this 2 arrow which goes between the 1 arrows. And so we can sort of see where this motivation comes from on the next slide, hopefully, if it goes across. Yeah. So if we can write, at least for small 1 categories, we can sort of draw this picture like this. And what we're saying here is that this is sort of at least the underlying data of the category. So this doesn't capture any of the sort of identities or composition, but we have this set C0 of objects or collection. Yeah, so if we stick to small categories for now, then we have this set C0 of small objects here, this set of arrows, and each arrow has a source and a target, or a domain and a codomain. And now for globular sets, all we really do is we extend this picture upwards like this. So we've got a set of objects again, and a set of arrows, which have a source and a target. And now we say we've got a set of 2 arrows or 2 morphisms or 2 cells. There's lots of different names, but these also have a source and a target in this set of 1 arrows. And now if we remember this picture from before, the sort of key thing that's happening in this picture is that if we look at this 2 arrow and we take its source, which is this 1 arrow, and we take its source again, which is this dot, then this is the same as taking the target and then taking the source. And similarly, if we take the target, then the target, this is the same as taking the source and the target. And how this manifests is if we go to the definition, we get these relations here. So effectively, these maps, we have some equalities between these maps. So all this is really saying is what I said on the previous slide, which is that effectively these, it's effectively what makes these things shapes like globes. And so, yeah, so just to go over the definition a bit more slowly. So we say a globular set, we have a set Gn for each n. So we have one for each, that's for each n in natural numbers. And we have maps that go from the source and target maps that go from the higher sets to the lower sets, and they have these globularity conditions. And just to add a bit of notation, we're going to say that we're going to sort of use normal category theory notation and say that we've got f from x to y, just meaning that we've got some object f and its source is x and its target is y. So that these s and t are, I probably should have put some subscripts here, but a lot of the time we'll leave it out when it's sort of obvious, because you can usually only apply one of them. And then lastly, I'm going to call the objects the 0 cells, the morphisms the 1 cells, and going onwards. So the elements of Gn will be n cells. So I think that covers at least what a globular set is. And now I want to talk a bit about composition in globular sets. But before this, I want to give some examples apparently. Sorry, I forgot this slide. So so some examples of globular sets. As we sort of saw, we got the order in 1 categories can be viewed as this sort of truncation. This was sort of the base of this big chain of sets going upwards. And in the same sort of idea, anything's 2 categories, 3 categories, so on, all fits into this scheme, or at least how I've normally seen 2 categories defined fits into this scheme. And then also for anyone who's done a bit more of this stuff, you've probably seen that monoidal categories and braided monoidal categories can sort of be seen as 1 object versions of 2 categories and 3 categories. So basically the idea is that lots of different things fit into this scheme. And lastly, just to give a bit of a different example, for anyone who's familiar with type theory, then the ideas of Martin-Loeb type theory or book homotopy type theory fit into this. And the way they fit into this is that we can say, so if we have a type A, then effectively we're saying that we have elements of, or not elements, terms of type A are the 0 cells, and then we have an identity type which gives you the higher arrows. And I think if you've seen this before, that will make sense. And if you haven't seen this before, this isn't, anything I draw now is not going to help. So I think we should just move on. So yeah, I now want to talk about talk more about composition. And I just want to introduce this idea of unbiased and biased composition, because I'm not sure that everyone must have heard of this before. So yeah, the thing I want to stress is I'm going to go over this for normal 1 categories. And the idea is that our normal definition of 1 category has biased composition. So what does this mean? Well, what it means is that we've just defined a binary composition and identities, and we've not defined any other types of composition. And we're just hoping to be able to build these other types of composition from what we had from our binary composition. So we can ask different questions. Could we have just defined the category of a ternary composition? And yes, it would work. It's not I don't think I've ever seen anyone do it, but there's no reason we couldn't really. Does a unary composition make sense? Again, it's sort of, I've flipped my tablet. Again, it does make sense, but there's also not much, I can't see a point personally. Does a nullary composition make sense? Yes, I think this actually gives you the identity. But the point is, we could actually define a category to have all these types of composition. So we could have a composition for every sort of n chain of arrows. And if we had done that, that would have given us an unbiased definition. So we allowed every possible composition operation that made any sense. And then in a biased definition, we're only allowing a subset. So our normal definition, as I said, we're only allowing a binary compositions. And maybe in this 1 category example, this isn't that interesting, but as we go a bit higher, we get a lot of different sorts of composition that we're allowed. And I'm hoping you'll agree with me that it gets a bit more interesting. So to get this, we should look at some of the composition operations we get in globular sets and infinity categories. So I'm going to first look at the two-cell composition. So this should really be this two. These are two. I guess it is two cells, but they're also two cells. If that's a bit of a tongue twister, but so yeah, the idea is that there are multiple ways we can now compose these. So we've got this first example, which is we're composing along a one boundary. And why am I saying this? It's because this is the boundary between these two cells here, and it's a one arrow. We can also compose along a zero boundary. Then we get the sort of boundary part is this circle here. So these are usually written as sort of vertical composition and horizontal composition, but I want to stress that the important thing we're focusing on this talk is the dimension of the boundary that sort of separates these two. So here we had a one cell and here we had a zero cell. And now I'm going to give a load more examples if the next slide loads. So for example, if we want to compose two free cells, we now have three options. So here we've got a two cell as the boundary, here we've got a one cell as the boundary, and here we've got a zero cell as the boundary. But as before, we're not really limited to binary compositions. And in fact, we can allow lots of wacky stuff. So for example, over here, we've got a whiskering composition. So we've got a one cell here and a two cell here, and we're able to compose these like this. And yeah, so it's not necessary that we have to say, oh, we've got two cells of the same dimension, we want to compose these. We can do other stuff. And just as sort of a example here, we can really allow any sort of things that are going to line up together. And this is this makes sense as a composition. And so more generally, I've written that I'm going to talk about pasting diagrams on this slide, and I'm not going to try and define them really vigorously, but the idea is that a pasting diagram is going to be a globular set that represents some composition. So effectively, any of these compositions I've given so far are examples of pasting diagrams, and the way I want you to think about it is a pasting diagram is some viable composition we can do in a globular set. I'm going to give a bit more of a rigorous definition a bit later, if I have time, hopefully. So yeah, now I want to get on to the last part of my talk, which is what I've actually done. So all of this has just been definitions, basically. So, and unfortunately, I'm starting with another definition, but so this is, we're defining now a class of compositions. So we're saying a stable binary composition is, it's going to be a binary composition, and it's going to be only the compositions where we're composing along this boundary here. And I realize that might not mean much, so we're going to write a few examples. So as a first example, if we take the vertical composite of two cells, then this is stable as we've got a two cell at the top. So we've got n equals 2, m equals 2, and the boundary equals 1, which is equal to the minimum of n and m minus 1. Similarly, if we take this whiskering we saw earlier, then this is also fine because we've got now a one cell and a two cell, and we're composing along a zero boundary, so that also adds up. And then as a counterexample, this horizontal composition we saw, this is not stable as it's two cells and we're composing along a zero boundary. So just to give an idea of why I've called these stable, the idea is that if we drew these geometrically as string diagrams, then the stable ones would sort of not be changed under small deformation. So just to show this, if you don't know what a string diagram is, then don't worry, this isn't going to affect anything else in the talk. The idea is if we have a string diagram that looks like this, I can deform this a little bit and it's still going to represent the same composition. Similarly, this one, I can deform this as much as I like and it's still going to represent the same thing. But with this one here, I've got something that looks like this. And as soon as I shift one of these dots off of the same line, it's now representing something else, and probably something that looks like this. I'm not sure if this diagram will make sense, but it'll turn into sort of a vertical composite of two whiskerings, and that's, so yeah, that's a different composite. It's an equivalent, so it'll be equivalent in an infinity category, but for the purpose of this talk, it's a different way of composing these two morphisms. So right, so basically what have I done? So I guess my claim first is that these stable compositions are enough to build up every other composition. So in the same way that the binary composition in one category was enough to build up every composition in one category, I'm saying that these are a large enough class of compositions to get everything. But unfortunately, proving definitions of infinity categories are equivalent is notoriously hard. So instead, we've proved this theorem. So we said that every pacing diagram we can see it as a tree of these binary stable composites, and that this realization has some nice properties like respecting the source and target maps. So now I want to spend the last 4 or 5 minutes I have going through a proof sketch of this theorem, and just to give an idea of how it works. So before we can really get anywhere with solving this theorem, we need to basically know what a pacing diagram is, or have some way to attack what a pacing diagram is. And luckily there's this nice inductive characterization, at least, which at least the first time I've seen it is a paper by Finster and Mimram. I'm happy to share that later. But the idea is that we define inductively these pacing diagrams with a focus, and then we're going to say a pacing diagram is something with a 0-dimensional focus. And so the main operations are a singleton globular set is a pacing diagram. We can do the composition of one object, not that it means a lot. We can then, if we've got a pacing diagram with a focus, we can adjoin a new thing onto it with a new target. So this is the sort of thing we're joining with this fresh target here. And this goes from whatever the focus was to the new target. And lastly, if we've got the focus, we can restrict the focus to its target. So I'm going to go over at the end a big example of this, but I'm just going to rush through the definition. So the idea is that we've defined this replacement. So this replacement effectively replaces the rightmost variable in some tree of composites. Then this allows us to define this horrific looking thing, but it's not too bad once you get your head around it. So the idea here is that we've got a pacing diagram and we want to define this tree of composites. So we've got if it's a singleton, that's fine. We just return that one variable. If we've got this extension here where the new thing we're extending by is the maximum dimension we've had so far, we can just replace this in the thing we had. And if it wasn't, then we have to do this funny expression. But I think all this will be clearer with an example. So I'm just going to go on to an example. So let's say we wanted to get the stabilized form of this composition, which we already know, we've already seen this is not this is not a stable composition. So firstly, what are the steps of this inductive buildup? So what we have is that the first step is that we say this dot here, I haven't actually drawn the dot, but this place where a dot should be is a singleton pacing diagram. We then extend by this map here. I'm going to give these all some names. Oops. Y, Z, F, G, H, I, A, B. Sorry, that's a bit messy. But then we extend by F and Y here, and we're left with focus F. Now we extend by this A, so we add in H and A, and we have focus A. We now restrict twice the focus to H, then Y, and then we carry on the same thing. So we add this G and Z, then add this B and I, then restrict twice again, and then we say we've got a pacing diagram. So what are the steps to trying to build this composite? So the first step was we start with the singleton. So we start with this X. Now we've got an extension step. So we're extending by F and Y, and this F is a higher dimension than anything we've seen before. So in this case, I'm not sure if you remember, but in this case, we took what we had before and we just replaced the rightmost variable by the new one. So this just replaces this x by an f. Next, we have another extension step, and again, it's the highest dimension we've seen. So we just replace this f by an alpha. And now we get something a bit more interesting, because we're after some restrictions, which we're not worrying about for the stabilized form, we extend by this g, and this is a lower dimension. So in this case, we needed to compose, and it ends up that once we work through this formula, we compose with g. And so this will actually be along a zero cell, and this is a stable composition. And then finally, we extend also by this b, and this is also not the highest dimension we've seen so far. So we have to do, we're composing again, this time along a one boundary. And the way we did this was we took the target of what we had so far, which is h.g, and then did this replacement, and we get h.b here. And this is sort of the final thing we're left with. And just to draw this out, this gives this composition that we saw earlier, which looks something like this. So sorry, I'm realizing I'm running out of time, so I'm just going to go over the conclusion, which was, so the things I've done is introduce this notion of a stable composite, define a translation from pacing diagrams into these stable composites, or showing how to build them up from this. And the translation has some nice properties, like it respects boundaries, and the term you get was equivalent to the one you started with, and things like that. And then just to sum up, what I aim to do in the future is that proving that this really is an equivalence. We've got sort of some ideas of how to tackle that, but they're still in early stages. And it would be nice to generalize some of the work so that I could basically prove that lots of different composition schemes work instead of this one particular one. But yeah, I think that's where I'm going to end. Sorry I had to rush through the last section a bit. I think I spent a bit too long at the start, but thank everyone for listening.
Okay, thank you, Alex. I think we can thank the speaker.